Hello and welcome to Tillage Edge with me, Michael Hennessy. This is your regular update for all your tillage news and advice. Soils are the most important resource we have as a human race. Without productive soils, there wouldn't be any farming or food production. Understanding the core functionality of our soils is fundamental to a management strategy for a long-term productive soil. Over the next 4 episodes, we will explore the fundamentals of soil, how to measure soil components, and how soils can be improved over time. On this first show, I'm joined by Professor Mike McLaughlin, originally from County Antrim, who is now a research professor in the University of Adelaide, Australia, and an Adjunct Senior Research Fellow with Teagasc. Professor McLaughlin established the Fertilizer Technology Research Centre at the University of Adelaide in 2007, supported by the Mosaic Company, and has conducted many projects through the Australian Rural Research Corporation and the Australian Research Council. Mike has also worked with our colleagues across Teagasc on various different soil components within Ireland. Mike, you're very welcome to the podcast. Firstly, Mike, you might just give us a little bit of background to your career so far.
I came out to Australia about almost 40 years ago now, actually, to study at the University of Adelaide. And I've stayed ever since. I've moved away from Adelaide, so I worked in Canberra and Melbourne for a while, but came back to Adelaide about 30 years ago and been here since, working in CSIRO, which is the government research organisation, and then more recently in the university teaching soil science and doing research in soil fertility.
Okay, so the research you were involved in, Mike, that was around kind of the whole soils bit around the soil science bit, or was there anything in particular in that area you were working in?
Yeah, well, look, I came out here to do my PhD, in fact, and my PhD was looking at how phosphorus cycles through the microbial organisms in soil and how it goes into the organic P fraction and gets released and taken up by plants. And then over the years, I've worked on various things. So then I was working on acid soils, looking at phosphorus chemistry and acid soils, and then moved into micronutrients for a while. And more recently, I've been working with a lot of work on sulfur. And back to phosphorus again, and a little bit of work on nitrogen transformations now as well.
Okay, so the whole gamut of stuff then, really, from one side to the other then, really, for the most part.
Yeah, and soil pollution as well, looking at heavy metals in soil and stuff like that. So, but yeah, recently it's mostly focused around fertilizers and soil fertility.
I suppose we might just start maybe at the very start, given the fact that soil is made up of, a good few components that aid the functionality. Clay, silt, and sand, and organic matter, just to name a few. But in terms of those kind of major ones, which are at the core of how soils work, which ones are, I suppose, the most important and the ones that actually add most to the functionality of soil?
Look, I wouldn't like to pick a winner in this. I think it's a bit of a team. So obviously clay, silt, and sand, and organic matter are the solid components of soil, that the things you see actually when you look at a soil is clay, silt, sand, and organic matter. And the clays are obviously very important because they've got a lot of the nutrient holding capacity in soils and a lot of the water holding capacity. And similarly, organic matter's got a lot of the nutrient holding capacity and water holding capacity. But it's really the interaction of clay with the silt and sand and the organic matter that makes up soil fertility in a physical sense as well as a chemical sense. So if you take any one of them away, you end up with a problem in terms of agricultural production. So it really is a team activity in soils. As I said before, clays are critical because they're the largest surface. They're very small particles, so they have a very big surface area, and they've got a lot of surface charge, and that helps to retain nutrients in soil from leaching. And organic matter, originally organic matter comes from the natural vegetation that's on the land, but then we add organic matter to soils as well. And don't forget, when you grow a crop, about 40 to 50% of the carbon goes below ground. So if you're taking up, you've got 11 ton or a 12 ton wheat crop, and you've got the straw on top of that, maybe 20 tons or 25 tons of biomass, you've got 12 to 15 tons of carbon biomass going below ground as well. So there's a huge input of carbon through agricultural production that we forget about. Agricultural production doesn't take carbon away from soils necessarily. The production part of it puts it into soils. it's the tillage part of it we've got to be careful with, because that tends to mineralize the organic matter.
Okay. And from the point of view, then I suppose when you delve in a little bit deeper to soils, most farmers would be very familiar with pH. How does the pH influence or vary on those different elements, and how important is that in terms of helping the availability of the nutrients within that soil?
pH is often, soil acidity or alkalinity is often called the master variable in soils, because it controls the availability of so many nutrients for crop growth, and also can control the activity of microorganisms in the soil. So when soil pH is low, you've got problems in that low pH actually dissolves up clay in soils. So clay, a lot of clays are aluminosilicate minerals or aluminium hydroxides even. So it's the composition of the actual clay itself is aluminium with silicon. And if you get a very acid soil, you actually break the clay mineralogy apart, and the aluminium gets released into the soil pore water, which can make it toxic to plant roots, but it also allows the aluminium to move out of the soil. So effectively, you're leaching your clays by low soil pH. That low pH also changes the charge on the soil particles, so the clay and the organic matter, and that can affect how the soil holds nutrients. So acid soils in particular are going to bind phosphorus very strongly because of that very reactive aluminium. And also they're going to bind some of the microelements, for example, things like molybdenum, which is important for nitrogen fixation, is bound very strongly in acid soil. So it affects that availability of nutrients. You don't want a soil to be too acid, and you don't want it to be too alkaline. On the alkaline side, you get in trouble with trace elements. The trace elements that have got a positive charge on them. So that's things like zinc and copper and manganese. And they're going to be a problem in very alkaline soils because they get bound very strongly, and so does phosphorus. So at the two ends of the pH spectrum, you've got issues with nutrient availability. And also microorganisms aren't very happy when it's very acid or ultra alkaline as well. So we really want to keep soils in that mid pH band between pH 5.5 to 7.5 is sort of the sweet spot for pH.
Okay, and even up as far as 7.5, I suppose most people here would probably get a little bit worried once it gets up as far as 7 in terms of the availability of P. But would you be happy enough in up as far as 7.5 in those circumstances?
Well, you see, in Australia, we've got soils of pH up to 9.5. When I'm talking pH extremes, that's
okay.
You've got major problems when we've got huge areas of soils of pH 8.5, which is a major problem for phosphorus availability. But yeah, once you get above 7.5, then that's where the phosphorus availability starts to dip off. So, and usually that's soils that are naturally developed on limestones, or if you've over-limed a soil, if you've added a lot of lime to a soil, you're going to have lots of reactive calcium carbonate. And that can be a problem then for phosphorus availability and trace elements.
And then when it comes to, say, a farmer has a highish pH soil, as in 7 or maybe up as far as 7.5, we don't have probably too many soils here that are too much above 7.5. Would it make any difference the type of phosphate that's used, whether it's diammonium phosphate or triple superphosphate? Does the source really make any difference in terms of trying to help the availability of that phosphate through the season in those higher pH soils? Yeah,
in a higher pH soil, triple superphosphate is basically calcium phosphate, whereas DAP, diammonium phosphate, is ammonium phosphate. So very different reactions in the soil when the granules first go into soil. The DAP, initially it's slightly alkaline, and it's interesting actually, DAP slightly alkaline reaction around the granule, but then because of the ammonium in there, as that gets converted to nitrate, that will acidify the soil, which on a high pH soil is good because it brings it more into that sweet spot. Interestingly, TSP is acid to start with because of residual phosphoric acid in the granule, but then it's becomes quite alkaline over time because of the reaction with the soil, and there's a lot of calcium phosphate in the product itself. So because you get calcium in the soil and calcium in the product, that can reduce the diffusion of P a little bit. So it's a small effect in terms of the chemistry, but it has been shown that applying ammonium with phosphorus is very beneficial to crops. There's a synergy of the nitrogen with the P being placed together. So the ammoniated phosphates tend to do better than TSP. Obviously, if you've got a legume crop that doesn't require much nitrogen, TSP is probably more preferred because you don't need to pay for nitrogen.
Okay. And in terms of the, when it goes on, it turns slightly acidic over time. And when that acidity reduces, then how long does it take for that phosphate to bind in those high pH soils? As in, I suppose thinking, could a grower expect to see some of that phosphate still being available 3 or 4 months later?
Yeah, look, the reaction when a granule goes in soil is really very, very quick initially. So the granule dissolves almost immediately within 24 to 30 hours. Most of the phosphorus would have come out of the granule itself and moved into that zone of soil around the granule. So initially you get reactions called precipitation reactions occurring. And in an alkaline soil, it's calcium from the soil precipitating with the P. And effectively you're turning it back into, first of all, it's triple superphosphate, but then it becomes other less soluble calcium minerals. So that precipitation can happen quite quickly. But then over the longer term, the soil will tend to dissolve up some of the precipitates, and it gets held by other mechanisms in the soil, a surface reaction. And that surface reaction basically is stronger with time. So it's one of the unfortunate things with phosphorus is the binding does increase with time in a low fertility soil. So we do have to build up the soil phosphorus bank, if you like, because of that binding. In a lot of cases, it's not irreversible, I should say. Some people tell you there's irreversible binding. It's not, because you do get some of the phosphorus back from previous applications. It might be a small percentage, but if you apply phosphorus over decades, or in some places centuries, all those previous phosphorus applications do contribute to the crop uptake eventually. So the actual efficiency of P use isn't as low as we think. So if we measure efficiency of P use in a single year, and we can do that using tracers, we might find only 10 or 20% of the P gets into the crop. But if you look over, say, a 50-year period, the P balance efficiency of a system might be 80 to 90%, where you're putting on 20 kilograms of P and you're taking off 18 kilograms of P in the grain, and you're in a sort of an equilibrium situation. Quite often, that's in Australia, that's called the maintenance phase, where you've got the soil into a balance with the input equals the offtake. So on that long term, the P efficiency is quite high. In the short term, from that single granule, it's quite low. So yeah, you need to be aware that phosphorus efficiency isn't quite as low as we're made to believe sometimes.
Okay, so I suppose that really comes down to, and as you say, the background phosphate, the background level needs to be there in the first place. And I suppose the tricky thing there is what's the sweet spot in terms of that background level, so you could just do that bare topping up type scenario and you get this 80% efficiency.
Well, yeah, that's why we do soil testing. I mean, that's why it's critical to do soil testing for phosphorus availability, because if you've got a high soil test value, and you've got the 4 tiers in Ireland, if you're in the top tier, you probably need less or no P. And if you're in the very first tier, very low phosphorus availability in the soil, you obviously need to add a reasonable chunk of P to get the crop up to its full potential. So the point of soil testing is to get a measure of that availability of P from past applications. For example, at the moment, phosphorus prices are quite high. So a lot of farmers are not adding phosphorus to soil because of the cost. If that went on for decades, you would slowly see soil P-test values decline, and you would slowly see crop yields decline because the availability would slowly decline over time.
Thanks for that, Mike. Really interesting information there. And we will continue this next week, where we look at some potash fertilizer types, soils which fix P and K, and also how well trace elements can be taken up by leaves of plants. So finally, don't forget, if you enjoyed the podcast, then recommend it to a friend or colleague. And as always, rate, review, and follow on Apple Podcasts or Spotify so you never miss an episode. And for more information, go to teagasc.ie. I'm Michael Hennessy. Thanks for listening, and I'll be back next week with more tillage news and advice.